Yes, a true RMS ammeter and a true RMS voltmeter can be used in place of a wattmeter under certain conditions. Firstly, the voltage and current waveforms must be sinusoidal. This is because wattmeters measure real power, which only exists for sinusoidal waveforms. Secondly, the load must be balanced, meaning that the phase angle between voltage and current is zero. Thirdly, the ammeter and voltmeter must be connected to the same reference point in the circuit. Once these conditions are met, the real power, measured in watts, can be calculated using the following formula: power equals voltage RMS times current RMS times cosine of the phase angle. Since the phase angle is zero for balanced loads, the formula simplifies to power equals voltage RMS times current RMS. The accuracy of measuring power using an ammeter and voltmeter depends on the accuracy of the instruments. This method is not suitable for measuring power in circuits with non-sinusoidal waveforms or unbalanced loads. The readings may be misleading or inaccurate in such cases. As an example, if a true RMS voltmeter reads 120 volts and a true RMS ammeter reads 2 amps, and the load is balanced with a sinusoidal voltage, the real power is power equals 120 volts times 2 amps, which equals 240 watts. It is important to understand the theory behind power measurements to properly apply these instruments. Wattmeters directly measure the real power consumed by a load, taking into account both voltage and current, as well as the phase angle between them. This is especially important when dealing with alternating current circuits where the voltage and current may not be perfectly in phase due to inductive or capacitive loads. True RMS instruments are essential for accurately measuring voltage and current in circuits with non-sinusoidal waveforms. Standard voltmeters and ammeters are typically calibrated to read the RMS value of a pure sine wave. However, many real-world waveforms are not perfectly sinusoidal, containing harmonics and other distortions. True RMS instruments are designed to accurately measure the RMS value of these distorted waveforms, providing a more accurate representation of the actual voltage and current levels. When using an ammeter and voltmeter to calculate power, you are essentially using Ohm's law and the power formula to indirectly determine the power consumption. Ohm's law states that voltage equals current times resistance, and the power formula states that power equals voltage times current. By measuring the voltage across and current through a load, you can calculate the resistance of the load and then use the power formula to determine the power consumption. However, this method assumes that the load is purely resistive and that the voltage and current are in phase, which is only true for balanced loads with sinusoidal waveforms. In circuits with non-sinusoidal waveforms or unbalanced loads, the voltage and current are not in phase and the power factor is less than 1. The power factor is a measure of how effectively electrical power is being used, and it is defined as the cosine of the phase angle between voltage and current. When the power factor is less than 1, it means that some of the current is not contributing to the real power consumption, and it is instead circulating back and forth between the source and the load. This circulating current is known as reactive current, and it is caused by inductive or capacitive loads. To accurately measure power in circuits with non-sinusoidal waveforms or unbalanced loads, you need to use a wattmeter that can measure the real power, which is the power that is actually being consumed by the load. Wattmeters use a more sophisticated measurement technique that takes into account the phase angle between voltage and current, providing an accurate reading of the real power regardless of the waveform or load characteristics. In summary, while it is possible to use a true RMS ammeter and a true RMS voltmeter to estimate power in certain ideal conditions, it is generally not a substitute for a wattmeter in real-world applications. Wattmeters provide a more accurate and reliable measurement of power, especially in circuits with non-sinusoidal waveforms or unbalanced loads. Always use appropriate safety precautions when working with electrical circuits and equipment. Make sure to de-energize the circuit before making any measurements or connections, and use insulated tools and equipment to prevent electric shock. If you are not familiar with electrical safety procedures, consult with a qualified electrician. Now let's explore some more details on the conditions and limitations of using an ammeter and voltmeter as a wattmeter. When we say sinusoidal waveforms, we mean that the voltage and current signals vary with time in a smooth, repeating pattern that resembles a sine wave. In a purely sinusoidal waveform, there are no harmonics or other distortions. This is an ideal condition that is rarely found in real-world applications, but it is a necessary assumption for using the ammeter-voltmeter method to accurately measure power. Harmonics are multiples of the fundamental frequency of the waveform. For example, if the fundamental frequency is 60 Hz, the second harmonic would be 120 Hz, the third harmonic would be 180 Hz, and so on. Harmonics can be caused by nonlinear loads, such as electronic devices, switching power supplies, and fluorescent lighting. These nonlinear loads draw current in a non-sinusoidal manner, which creates harmonics in the voltage and current waveforms. When harmonics are present, the RMS value of the waveform is higher than the value that would be expected based on the fundamental frequency alone. This is because the harmonics contribute additional energy to the waveform. True RMS instruments are designed to accurately measure the RMS value of waveforms with harmonics, while standard instruments may underestimate the RMS value. A balanced load means that the impedance of each phase of the load is the same. In a three-phase system, this means that the impedance of each of the three phases is equal. When the load is balanced, the current in each phase is also equal, and the phase angle between voltage and current is the same for each phase. This simplifies the power calculation, as the total power is simply 3 times the power in one phase. An unbalanced load occurs when the impedance of each phase is not the same. This can happen when one or more of the phases is loaded differently than the others. For example, if one phase is connected to a large motor while the other phases are connected to smaller lighting loads, the load will be unbalanced. When the load is unbalanced, the current in each phase is not equal, and the phase angle between voltage and current is different for each phase. This makes the power calculation more complex, as you need to calculate the power in each phase separately and then add them together. The same reference point is where both the ammeter and voltmeter are connected to the same point in the circuit to ensure that they are measuring the voltage and current for the same load. This is important because the voltage and current can vary at different points in the circuit, especially in circuits with long wires or multiple loads. If the ammeter and voltmeter are not connected to the same reference point, they may be measuring different voltage and current values, which will lead to an inaccurate power calculation. The formula power equals voltage RMS times current RMS times cosine of the phase angle is a general formula for calculating the real power in an alternating current circuit. The voltage and current values are the RMS values, which are the effective values of the voltage and current. The phase angle is the angle between the voltage and current waveforms. The cosine of the phase angle is known as the power factor, which is a measure of how effectively electrical power is being used. When the voltage and current are perfectly in phase, the phase angle is 0, and the power factor is 1. This means that all of the current is contributing to the real power consumption. When the voltage and current are not in phase, the phase angle is non-zero, and the power factor is less than 1. This means that some of the current is not contributing to the real power consumption, and it is instead circulating back and forth between the source and the load. The circulating current is known as reactive current, and it is caused by inductive or capacitive loads. The accuracy of measuring power using an ammeter and voltmeter depends on the accuracy of the instrument. The accuracy of the ammeter and voltmeter is typically expressed as a percentage of the full-scale reading. For example, an ammeter with an accuracy of plus or minus 1% of full scale will have an error of plus or minus 1% of the maximum current that it can measure. When using an ammeter and voltmeter to calculate power, the error in the power calculation is the sum of the errors in the voltage and current measurements. For example, if the voltmeter has an accuracy of plus or minus 1% and the ammeter has an accuracy of plus or minus 1%, the error in the power calculation will be plus or minus 2%. This method is not suitable for measuring power in circuits with non-sinusoidal waveforms or unbalanced loads because the voltage and current are not in phase. In such cases, a wattmeter is required to accurately measure the real power. Additionally, the presence of harmonics in non-sinusoidal waveforms can further complicate the measurement and lead to inaccurate results if using only an ammeter and voltmeter. The readings may be misleading or inaccurate in such cases. It's important to be aware of the limitations of the instruments and the potential for errors when using this method. It is always best to use a wattmeter when measuring power in circuits with non-sinusoidal waveforms or unbalanced loads. Consider a scenario where a true RMS voltmeter reads 120 volts and a true RMS ammeter reads 2 amps, and the load is balanced with a sinusoidal voltage. In this case, the real power can be calculated as power equals 120 volts times 2 amps, which equals 240 watts. This calculation assumes that the voltage and current are perfectly in phase and that the load is purely resistive. In real-world applications, these assumptions may not always be valid, so it is important to be aware of the potential for errors. True RMS meters are designed to accurately measure the RMS value of non-sinusoidal waveforms. These meters use sophisticated techniques to sample the waveform and calculate the true RMS value, taking into account the effects of harmonics and other distortions. True RMS meters are more expensive than standard meters, but they are essential for accurately measuring voltage and current in circuits with non-sinusoidal waveforms. It's important to emphasize the significance of understanding power factor in alternating current circuits. Power factor is the ratio of real power, measured in watts, to apparent power, measured in volt-amps. It indicates how effectively electrical power is being used. A power factor of 1, or unity, signifies that all the power supplied is being used to perform work, characteristic of purely resistive loads where voltage and current are in phase. However, inductive loads, such as motors and transformers, and capacitive loads, like capacitors used for power factor correction, cause a current to lead or lag the voltage, resulting in a power factor less than 1. This means that some of the current is reactive and does not contribute to doing work, leading to inefficiencies and increased energy costs. Utility companies often charge industrial and commercial customers based on their power factor, incentivizing them to maintain a high power factor to minimize losses and improve grid stability. Power factor correction techniques, such as adding capacitors to the circuit to offset the effects of inductive loads, can improve the power factor and reduce energy costs. It is also important to consider the impact of harmonics on power quality. Harmonics are multiples of the fundamental frequency of the alternating current waveform and can be caused by nonlinear loads such as electronic devices, switching power supplies, and variable frequency drives. Harmonics can distort the voltage and current waveforms, leading to increased heating in electrical equipment, interference with communication systems, and malfunctions in sensitive electronic devices. Harmonic filters can be used to reduce the levels of harmonics in the electrical system and improve power quality. When working with electrical circuits, it is crucial to adhere to all safety regulations and guidelines. Always de-energize the circuit before making any measurements or connections, and use insulated tools and equipment to prevent electric shock. Wear appropriate personal protective equipment, such as safety glasses and gloves, and be aware of the potential hazards associated with electrical work. If you are not familiar with electrical safety procedures, consult with a qualified electrician. Remember that electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself and others. Consider the implications of using different types of meters for power measurement. Analog meters, while simple and inexpensive, have limitations in terms of accuracy and resolution. Digital meters offer higher accuracy, resolution, and features such as true RMS measurement and data logging. However, digital meters can be more complex to use and may require a power source to operate. The choice of meter depends on the specific application and the required level of accuracy. Additionally, it is important to calibrate meters regularly to ensure that they are providing accurate readings. Calibration involves comparing the meter's readings to a known standard and adjusting the meter, if necessary, to correct any errors. The frequency of calibration depends on the type of meter, the frequency of use, and the required level of accuracy. Understanding the limitations of the instruments and the potential for errors is essential for obtaining reliable power measurements. Always use appropriate safety precautions and consult with a qualified electrician if you have any questions or concerns. In summary, while using a true RMS ammeter and voltmeter can provide an estimate of power under specific conditions. A dedicated wattmeter offers a more accurate and reliable solution, especially in complex electrical environments. Understanding the nuances of power factor, harmonics, and meter accuracy is crucial for effective power management and safety.